Good morning. We are in this GIAN course, Combustion Theory and Applications. In today's lecture,
Hello.
कैसे
hello.
Udah, yang mau sih dikasih gitu. Dikasih. Hello.
change कर
Hello.
So, good morning. We are in the GIAN's course Combustion Theory and Applications, day 5. In this lecture today, we will talk about the part 2 of laminar premixed flame. In the previous lecture, we emphasized about the fundamental concepts of laminar flame, its characterizations, mathematical correlations through which we can compute the laminar flame velocity. Additionally, we found that certain correlations are important while we use that correlations as a function of pressure, temperature, equivalence ratio that characterizes the various characteristics during combustion, if it is a purely laminar flow. Then in this lecture, we will proceed further to bring out some other fundamental concepts that are of two categories. One is this flame arresting, second is flame stabilization. So, in our previous lecture, we emphasized that for a sustainable laminar flame, we need to have a favorable pressure difference or pressure and temperature conditions, so that continuous combustion is possible. In fact, we demonstrated that with respect to IC engine combustion for premixed air fuel mixture, in which it is emphasized that for a normal combustions we get a pressure trend as a function of time in a smooth manner. But however, when the favorable condition is not there, this is shown as a pressure pulses, sudden oscillations when the peak pressure is reached. So, this says that flame is already at elevated pressure and temperature and it has sufficient strength and it provides knocking. At the same time, if you want to bring this situation back, we need to have some other methods that we must avoid this knock through certain mechanism in which flame can be arrested. Of course, this flame arresting is not a typical phenomena for engines, but this arresting methods is very much required when you use this laminar flame for certain applications in terms of burners, cooking burners. So, this arresting method is required that when the flame should not travel back or create a flashback, for which we require to arrest the flame. In other words, we can say we must reduce its momentum to move further, to move backward. So, that is one aspect we also require. Second aspect also is that for cooking type of application, burner applications, we require a continuous stabilized flame. So, as long as we are supplying air and fuel mixture with appropriate compositions, we must get the flame. And second point is that the flame should sit on this burner surface. It should not be blow up that means it should not go above the burner, at the same time it should not create any flashback. So, that condition we call as flame stabilizations. So, there are certain techniques, this flame arresting method is dependent. First method is that we should know that why we what are the different criteria in which we generate the flame. Particularly when you look at the kind of flame, and this flame has to be flame is, let us say in this SI engine case, the flame is propagating and you need to arrest it. So, the arresting of the flame depends on the area in which this flame is moving. Then second is called as second method is that we can control these flame propagations by changing the composition of this unburned fuel air mixture. So, that thing we can talk about in the form of flammability limit. The first one we can talk in terms of geometry in which the flame is propagating. So, that is can be quantified by quenching distance. Another point is that whether we can create a flame or not, that depends on how much energy or ignition we are dumping into this charge. So, that is criteria is that it is a minimum ignition energy which is required to create that flame. That means, we are giving sufficient strength to the flame so that it can travel on its own. So, these are some of the methods which we can think of. Second is, in a classical way we try to extinguish the flame. So, extinguish method is simply dumping or cooling the flame through water, that is one aspect. So, when fire is burning we dump water so that it gets extinguished. Some cases we have fire extinguishers that can stop the flame propagations. So, which means that diluents such as water, chemical compositions, or in terms of fire extinguishers which are in the form of halogens, they can alter the chemical kinetics. So, basically in totality what we can say that the flame has to be extinguished under certain situations in which it cannot create the explosions. In other words, in a layman sense we can say by creating these concepts we are altering this chemical kinetics of the flame. So, this is our three basic methods which we are going to discuss. So, first thing that we talk about a term called as quenching. So, quenching term depends on a parameter what is called as quenching distance. This quenching distance is determined by observing the flame which is passing through a tube, so that it does not flash back for a particular tube diameter, which means if you are looking at a flame with the flame which is passing through between two parallel walls separated by a distance d, and looking at a flame which is in this domain. So, what you can see, there are two walls here and we can imagine as if there is a flame and this flame is moving up. This dotted line shows a kind of a wall which is in the vicinity of the flame, and we call this as a adiabatic wall, and this slot have total energy which is entirely stored in the flame and it is going up. So, when it is going up, it is trying to bring the charge into it and getting it combusted. So, that slow it is moving. So, there are two parameters here. One is called as delta, and this delta and other is the parallel wall in which the flame is moving. So, there is a correlation between this delta and D. So, there are two set of thumb rules which governs this ignition. First is that ignition will occur if enough energy is added to the gas to heat the slab of certain thickness for a steadily propagating laminar flow to adiabatic temperatures. So, once you put this minimum ignition energy, the heat which is liberated by these chemical reactions must be equal to the heat loss from this slab by the thermal conductions. So, basically what about heat is generated through this, it is getting taken out by the slab in which it is moving. So, that is the wall. When you imagine that when you are this type of flame is propagating in a combustion chamber on the engines, the chamber gets heated and we require cooling. So, that way but in this perspective what we say that heat which is generated, it is getting consumed by this. Now, if it has to be consumed, that means when if it does not consume, then strength of it goes up, and if it has to be consumed, because otherwise it will create a flashback. So, in this perspective, in this philosophy, there are two parameters that are taken into account. One is, suppose a flame which is entered in a slot which is separated by a distance d in this case, and we can define this adiabatic wall adiabatic flame thickness delta. So, adiabatic flame thickness delta means that flame is not getting cooled and entire energy is sitting there within certain vicinity of this wall, within the some vicinity of this thickness, and that thickness is very short, and that is called as flame thickness. And we also have, this means this is the maximum when you talk about adiabatic flame thickness, that means at this point flame has its maximum strength of heat within that volume, and this is this has to be distinguished or extinguished if the flame does not have to create a flashback. So, for that reason we can these walls should be placed in certain appropriate locations, so that, and that distance we call this as a quenching distance, which means it is the minimum distance we must have that the flame cannot traverse back. So, that way this quenching distance for the flame is always greater than the flame thickness. That means we cannot have so much this distance should not be so small, so that with respect to the flame thickness, it should be higher than that. And this flame quenching distance is also dependent on the other parameters like pressure and temperatures. Now, over the years the things are modeled in this case to find a suitable correlations between this quenching distance d and the adiabatic flame thickness delta. And here we define two parameters, one is this delta, one is this b, b stands as which is square root of b, and we have the square root of b into delta, delta is equal to your thermal diffusivity with respect to ratio between the thermal diffusivity and the flame speed. B is just a number, just to give just to make a correlation such that the quenching distance and delta is adjusted in such a way that B is taken in such a way that quenching distance and delta gets adjusted among themselves. And further, we also this thermal diffusivity is dependent on this pressure and temperature parameter, and which stands as a function which is a proportional to T to the power 1.75 by P. Then next point that we talk about in terms of flame arresting method is the flammability limit. For every fuel there are two limits in which we can initiate the combustion. You must have known that for IC engine operations we define this as a in terms of equivalence ratio. That means, engine normally operates in the equivalence ratio between 0.8 to 1.2, that is one part which is effective for engine point of view. But with respect to fuel point of view, it is also possible to initiate combustion at much more lower equivalence ratio, which is also less than 0.8 also, and it can also go above that 1.2. But what we are looking at the flammability limits, the minimum limit which is the lower limit for the lean mixture and maximum limit for upper mixture. We say that above this mixture we cannot make it with a very high fuel reach, so that combustion cannot be initiated, and we cannot have a number which is very lean for which combustion cannot be initiated. So, that is the limit, we call this as a flammability limit, and normally this flammability limit we say phi, which is written as phi minimum. Let us say I will put we have phi maximum, so there are two ranges, we have minimum and maximum, and in this we call this as a flammability limit. A mixture that sustains the flame is to be flammable, and just by adjusting this flammability limit. So, this particular curve talks about the flame temperature as a function of x, and it also we are looking at this delta, flame thickness delta, and here if you can see, initially when the combustion is initiated, temperature shoot off suddenly to a maximum value, and normally in this impulsive nature of the temperature rise, we define this adiabatic flame thickness, and the temperature reaches to a maximum. But however, the we can have adiabatic flame temperature which is much above that. And when you talk about this as a flammability limit, we have to say that somewhere we are operating this as phi, and this side we can have phi minimum, this side we have phi maximum. Then other important point what is to be noticed is that there is a instantaneous axial temperature rise which is along the central line of the tube. There could be possible conduction losses along the wall, and many times what happens, the cooling effect of the products gases create an adverse situation, which means is that why the you imagine that in a laminar situation premixed flame is moving forward consuming the charge. Sometimes what happens, the temperature shoots up and ideally temperature and pressure shoots up, and if the temperatures and pressure and shoots up in such a way that all those atoms they started to recombine. For example, nitrogen started to recombine with oxygen or something. So, it is expected that during the recombination they try to absorb energy. Through this energy absorption process during recombinations, it has a negative effect. That means, flame is getting cooled because the environment temperature drops down because due to reaction of recombination of atoms among themselves. So, that is called as cooling of product gases can create a negative temperature. Now, when sufficient heat is removed and quenching criteria is satisfied, then flame does not move further. So, the flame stops there. That means, flame is sufficiently cooled. In other words, we say we have arrested the flame. The next category of analysis of flame arresting method is ignition. So, ignition normally happens using a spark plug. The spark plug has certain dimensions of certain size or diameters, as if during a spark ignition what happens, we are we are creating a kind of and one simplest way we can create is a spherical frame. Through this thing, what we can say, we are dumping this energy through the spark plug, and for this spark plug has some diameter, and through this spark plug whatever maximum size we can create, that a spherical flame is based on its critical radius of the, which is with this spark plug we can create this maximum diameter of this spherical flame, that is called as critical radius of the plug, or in terms of flame point of view, that is the maximum diameter of that spherical flame. So, there are some correlations that how we can find out the critical radius of this gas volume. This is modeled in terms of spherical flame, and it depends. Basically, all you need to want to know is that what is the minimum ignition energy which is required by the plug. To get this, we require the information about this critical radius for this gas volume, and this correlation says that this critical radius is square root of 6 into alpha d times SL. So, here alpha d again depends on many parameters. alpha D depends on the pressure parameter. Here this SL, this depends on the ratio of unburned gas mixtures and burnt gas mixture. Then we have other terms, this in terms of this can be interpreted in terms of flame thickness, because alpha D by SL is delta. So, through this we can find critical radius for a gas volume as a flame thickness of this spherical layer of this gas. Then we need to find out, that is a relation what is through which we can find out how much minimum ignition energy required for a self sustained moving flame. So, that depends on this all these numbers, pressure, then thermal diffusivity, flame speed, temperature ratios and so on. And here RB stands as the gas constant. This RB is one parameter like Cp by Rb. Cp stands as the specific heat at constant pressure, Rb stands as gas constant for the burnt gas. This is calculated through ideal gas relations. Then next thing is we need to talk about this ignition analysis in terms of okay, this is already this I have already mentioned. The effect of pressure on the minimum ignition energy is the result of direct influence and indirect influence in terms of thermal diffusivity and flame speed. So, what we can say, this minimum ignition energy is inversely related to the square of pressure. So, if you actually see here PE, minimum ignition energy is a function of pressure, but the pressure is implicitly involved in the calculation of the flame speed. How? Because this flame speed is the function of Tu by T in, and which means that it also boils down that ignition energy is inversely related to pressure. Then we will move on to next segment, what is called as flame stabilization. In most of the combustion analysis, particularly cooking stoves and all, we require a self sustained flame to remain, so that we can say that flame is sitting on the burner face. So, there are two phenomena that can occur if there is flame is not stabilized. First phenomena is called flashback, second phenomena is flame lift off. That is mainly two critical aspects for the flat burners or cooking burners. We also say that flashback can occur when the flame enters and propagates through the burner without quenching. So, that means the flame does not see sufficient pressure difference to move forward. So, it travels backward. Now, while traveling backward, it sees that it does not have a sufficient slot diameter, and it follows through that slot in an effective manner. Through this we can get a flashback. So, for that reason, which means that appropriate quenching distance is not maintained. So, that condition is called as flashback. Other option is that through pressure difference, if the pressure difference is such that it does not that means we need to have, if it does not have a minimum ignition energy. So, through this, if he has more than this minimum ignition energy, it travels back. Also, this large volume which is there in the mixture, it can also create this explosion, because when it flash back, all of a sudden it sees the large volume of charge. Hence, this flashback has to be arrested. The other condition, that is what we call as flame lift off, which means this is a condition when the flame is not attached to the burner, it is sits at certain distance, and this is what we call as standoff distance. If this is your burner face and it is setting some height, so this distance we call as standoff distance or lift off height. But however, this lift off condition has to be avoided, because that is not a case for flame stabilization. Why? Because this lift off situation allows the unburned gases to escape. That means we are underutilizing our charge. Although the lift off, flame lifts up to certain distance, but if it goes above that, it is difficult to create ignition. That means ignition is difficult to achieve for above the lifting limit. Then accurate control of position of lifted flame is difficult to achieve. Through this lifted flame, it will land up poor heat transfer characteristics. And when we have lifted flames, they are always noisy. The conventional cooking burners, you might say that we might have experienced about these cases when the flame is lift off, or we normally do not create, suddenly we switch off the burner and an abrupt noise pops up, which means that those cases are recalled as noisy situations. Now, let us talk about flame stabilization in terms of flashback. So, flashback, when you see this particular figure here, we see that there is a burnt gas and flame front is moving, and on this flame front we can say that at each particular point we can define certain velocities, that is on the flame front, but at the same time we can also see the gas velocity which is moving, and this profile can be linear, which means that at this wall the gas velocity is 0, and with when we increase when we go towards the center line, then this gas velocity is more. So, one point, that means these two vectors or these two forces, they try to interact each other. When they interact each other, it creates the dominance of one with other. If the dominance of flame front is more, then it suppresses this, and dominant of gas velocity higher, it pushes the flame. So, due to relative dominance between these two, we get this flashback, and of course, it is sometimes it may have, there could be a transient phenomena which arises, and with time it tries to settle down. And the next is and it also depends on the tube size in which the flame is propagating. So, hence what you can say, the controlling parameters for this flashback is same as that of dwell time, equivalence ratio, flame velocity, burner geometry, and so on. So, this is another figure which talks about the case study, just to give some trend of two types of flame, two types of fuels. One is a fossil fuel, methane, second one is hydrogen. So, basic difference while talking about or considering these two cases is that hydrogen has a large flammability limit, whereas methane has smaller flammability limit, which means in terms of equivalence ratio, there is a large window in which we can create the ignition for hydrogen, but there is a small window in which you create the ignition in terms of phi equivalence ratio. So, these two, and because of this reason we can say the the flame speed in hydrogen is about 5 times faster than the flame speed of methane. So, what it says here, this particular diagram, it is a generic plot, not in terms of quantitative manner, it is a generic plot. It talks about the gas input rate or fuel flow velocity with respect to primary air, fuel and with respect to percentage of final primary or theoretical air we consume. So, if you go along and if you show their trends, what it says is that we for a methane we have this flashback zone somewhere here, which means for flashback to achieve, we are in the our air requirement is very high, but in other case the and also we have fuel requirement is very low. So, that means that is the safe zone in which fossil fuels are operated, but that is not true for these things, because your flashback zone can happen any point with very small fuel flow input. At the same time, air requirement may be close to 60% we can have it, and air is anyway available for the charge. So, small quantity of fuel can lead to a flash zone area. This is not possible when we use the methane. Now, when we say that flame is getting lifted from the burner surface, we can find a trace in which through which that if you keep on increasing the gas input rate or fuel velocity rate with this, you will find that with increase in the fuel flow rate, the theoretical requirement is less. So, that means whereas in the and this number is somewhere within this 60%, whereas for hydrogen it is much more higher. Similarly, we have lower regime in which the flame shows a different color, like we have yellow color here, we have yellow color here, and this is possible with 20% and here also close to 40%. So, that way this gives you a domain in which we can design your area or geometrical area in of that burner port. So, here we have a large domain of design area for a stable flame, because that is what we require, and that domain that is a standard domain. Here we will have also for a stable flame, in this case we will also have a very much larger domain than this. Okay. That means for hydrogen lifting zone requirement is higher, whereas for methane it is lower, which means that we have a flexibility of larger burner area for hydrogen as compared to fossil fuel or methane. So, this is one kind of advantage, but however maximum possible area for hydrogen we can define this and here this, but there are detrimental effect if the flashback zone is taken into account. Or in general, the basic summary is that whatever size you or design area or you choose for a stable flame, either for either for methane or hydrogen, the main intention is that it should be it should have flash free zone during its operation. That is the requirement for a stable flame. Now, another situation I have emphasized here, that flame is tried to lift up. Lift up, which means it is this, why it is gets lift up, because flame has sufficient strength, it does not get enough oxygen from the charge and it gets oxygen from the diffusing air, which is outside the zone of, which is atmosphere. Assume that we have the burner face and flame gets lift up. So, there is a stand up distance between them. So, through this you have atmospheric air running into it and oxygen gets filled up. So, the flame plant gets enough oxygen to lift it further, but while lifting it further, if you see that at the same time you have gas velocity which is coming up. So, they either try to diffuse or they try to get these things here, but if this flame trump lifts up with a certain limit, then it can say that this input charge gets diffused outside without getting ignited, because the flame plant has already travelled further and the energy is not in the vicinity of the surface, it is somewhere outside. So, that way if you look at in terms of this velocity diagram of laminar flame, this alpha changes. So, alpha is no longer one particular thing is that this condition has to be satisfied for between unburnt gas velocity Vu and the laminar flame velocity SL. So, they do not match, which means flame gets lift up. So, there is a critical velocity at which flame gets lift up, and that when it crosses its critical velocity, we will have higher vertical flame lift up distance, and the flame until the beyond the above this burner surface. So, this is I have already explained, but the phenomena of lift up or blow up, that I need to emphasize. So, lift up, I told you that lift up is that flame is getting lifted from this burner and sitting at somewhere. So, that is the lift up. There is a situation called blow up. So, blow up means that the gas velocity at one particular time, this gas velocity does not see the flame in its vicinity, that means input charge velocity does not see it in its vicinity, and so it could not be ignited. So, when it does not get ignited, but it has a sufficient momentum to push the flame, it can push the flame, but it cannot ignite on its own. So, that way we say that flame blow up condition is achieved. Now, in heat transfer point of view, we say that this is a counter effect or for which heat or radiation loss to the burner tube. So, this view is analyzed the heat or radiation loss. So, ultimately this leads to a conclusion for methane and hydrogen is that the lift up operation for the flame varies as the function of primary air flow velocity, and methane flame is more towards lifting as compared to hydrogen, that is also true, because hydrogen has very high flammability limit, wide range of flammability limit, and of course, hydrogen has higher flame speed. So, this is all about I need to discuss with respect to the laminar flame analysis, and this particular at the end of this lecture I try to emphasize that some numerical problems which highlights for a flat flame which is sitting on a burner, and we need to calculate, and one case study which is done for a methane air mixture, and the condition that burner operates is 300 Kelvin and 6 atmosphere, and we need to find out what is the condition for flashback, what is the mixture mass flow rate. That means, you need to design this burner. When you try to design this burner, we are actually trying to find out what is the burner size and all. So, first step we need to find for methane air mixture what is their mass fraction of air and this mass fraction for fuel, and we need to find out also the density of onboard gas mixture to obtain this mass flux. And this particular equations data either you can use this dependence of flame speed as a function of pressure, and using this one can find out these things one by one. First is what is the mass flux, second how we can find out the diameter ratio, which talks about the conditions when we have a non-lifting case, and other we have a basically when the flame has to sit on this burner surface, other case is what is the maximum distance it can sit on this. So, this will give you the allowable tube diameter. Then another important problem that talks about the importance of flammability limit. For example, this says that in a corner of a room in a cylinder the propane gas leaks, and whether that leaking creates and can create an adverse situation or not. So, to find this case, what we need to know, first thing is that we have to, from the data table, we need to find the what is the minimum and maximum flammability limit we can find out, particularly for propane. This we obtain from data. Now, for these particular conditions, what is the value of phi which you need to find out. So, in this case you have given the size of the room, mass, temperature. We can use these ideal gas relations, find the pressure, and of course, we have atmospheric pressure. Through this we can find out the mass fraction for the fuel, and here the fuel is methane. Once you know the mass fraction, correspondingly we can find out the air fuel ratio. So, this is how we get air fuel ratio for this particular case. Now, again for methane air mixture, if you can look this balanced equation or complete combustion equation, we can find out the corresponding stoichiometric value, and for this case the stoichiometric value happens to be 15.6. So, through this what we can say, air fuel ratio and air fuel ratio actual and air fuel ratio stoichiometric. From this we can find out what is the equivalence ratio for this fuel which is getting leaked. That means, this mixture when it is leaking, it has the equivalence ratio 5, because when it is leaking, it is mixing with air, and it is mixing with air means at that case your equivalence ratio is 0.18. Then you have to cross check whether it falls in that flammability limit or not. So, that way one can say that, and in this particular case we say that mixture does not support the flame. So, this leaking cannot initiate a flame. When it cannot initiate a flame, we can say it is not a detrimental effect or adverse effect, or it does not lead to any kind of explosion. Sometimes also in our conventional cooking burners, we feel there is a leak through smelling, but that leak does not lead to explosion, because it is in very low flammability limit. And when the flame it crosses this, when it comes to this higher flammability limit, it can create some adverse situations. So, this is all about I need to discuss for today. Thank you. Yes, yeah. होता तो तार 3 तारिख आइदर 2 न 3 मु सेमती कहूँ चार्ज सियाडी जीव 2 3 दिन हमरा that is here no? That is you can tune but online people you coordinate that okay sir
Okay.
yeah
So
अरे इसको white screen करना white screen full screen नहीं 16 स्टार्ट
white screen. Perfect. I'm old school.
yeah no this is for recording
Yes, of course. Okay, welcome back. We will continue today laser diagnostics for combustion research after we have discussed yesterday mainly the reactors with focus on shock tubes and RCM. Today we will focus more on laser diagnostics itself, so application of laser methods to examine combustion processes. Of course, we have only 2 hours for this topic, so we will not go into all the spectroscopical details. Here we have to reference to fundamental lectures from other areas, but I would like to explain you at least different methods which can be used to examine specific details in a combustion or an ignition process. The advantage of laser diagnostics is, of course, we do not disturb our probe volume. If you use a temperature sensor, for example, and put it in the flow, of course, there is always an interaction with the system. If we use optical methods, we have then the advantage not to disturb the process. However, we need optical access, otherwise we cannot examine it. So we have to, of course, we have really different levels to consider. We can apply these techniques for complex gas turbines or combustion engines with some limitations, but more often, of course, we perform these measurements on lab scale experiments. We can examine atoms and molecules, but we can also examine larger molecules to examine soot formation. We have conventional absorption spectroscopy, so the extinction of light due to absorption, but we also have sophisticated laser spectroscopy, laser-induced fluorescence, Rayleigh measurements, Raman measurement, coherent anti-Stokes-Raman measurement, degenerate four-wave mixing. So there are a lot of nice abbreviation you can find in the literature with specific applications. Here we will focus only on the most important techniques. And at the end, it's not laser diagnostic, but of course it's diagnostics, so I will end with some slides concerning gas chromatography and mass spectrometry. Just some simple, just a simple overview here. So this we have seen yesterday already in a shock tube. You of course can use a pressure sensor to examine the process, and to get your specific signals. If you use several pressures along the pipe, you can measure velocity, and at the end wall, for example, when you reach the T5 zone, after a given delay time, you can measure the ignition delay time. This we can support with emission spectroscopy if we have an proper window applied to our investigation volume. So here we have the emission of OH star, for example, which is then detected by a photomultiplier and stored by a PC recorder. So, and we see here then, okay, the emission also gives us information about the ignition delay time, which is often a better variable to examine your results with numerical calculations. So hopefully today this video will work. So we can perform Schlieren measurements. So you see, we don't see. I'm sorry, I've tried it on my computer. I have reintegrated the video. Okay, we can live without it. Okay, the idea of Schlieren measurement is when you have density gradients, you have a flow with different densities, and you have density gradients, of course, and you have different volumes with different refractive indexes. So, and when you send light through these volumes at the boundary layer between the two different density volumes, your light is deflected, and what we have here is a typical setup. So we have a light source, we have a typical lens, and then another lens to collect the light. And here we have a knife edge, for example. So the idea is, of course, if the light is not disturbed, we won't see any influence here. But if we have hotter or colder zones, our light is deflected, so it's no longer in line here, and so some part of the light is here moving to the right, and this is then cut out with our night edge. So in our image we would see a darker area, or the other way around, if it's moved in this way, we would see a brighter area. So we see density gradients and can so visualize shocks, combustion processes. It's also possible to perform quantitative Schlieren measurements. So if you do it very precisely, you can also get information about the temperature field. So here's an example. So we have an early model for diesel combustion. So until in 1984, so it was assumed, okay, we have a jet of a liquid fuel. This vaporize, atomize here, and then we have a diffusion flame here in this area. So this is what they assumed. So here we have the diesel, here we have the air, and the flame takes place here in this area. So then here we perform Schlieren measurements in an optical engine. So we have one cylinder of an engine. Here we have optical access through a small window. Then at the bottom of the piston there is a mirror. We have another window here, and so the light is transmitted to the outside again, and we can collect collected with our camera here. So here you can see more in detail the setup. So the light is following this path here, and so we have possibilities to examine our diesel process, and these techniques then have shown finally that the classical model was wrong. So we don't have a classical diffusion flame here outside. So we have a fuel-rich premixed reaction zone here. So and combustion take place more or less all over here. And here we have the NOx formation and the soot formation, soot oxidation zone outside. So what is the ideal solution? What would the dream? So it would be nice if we can measure the interesting species time resolved, and of course radicals, transient intermediates, and even isomers could be detected, and this should be done for all interesting pressures and temperatures. So what can we do already? That's already a lot. Here you see a classical reaction pathway. On the left and on the right you see the soot formation process, starting with simple hydrocarbons plus oxygen. So here we can use absorption, fluorescence, emission, phosphorescence, chemiluminescence, LIF, laser-induced fluorescence, to examine the molecular level. Then we can use LIF for the larger PAH, and finally we have electroluminescence, laser-induced incandescence, and Mies scattering to examine the larger soot molecules. So I will explain all the background here in the following slides. And here, of course, this we have already discussed. We have the possibility to examine our interesting molecules, HO2, H2O2, H, RF, OH, RO2. So we have specific tools here to examine the temporal evolution during elementary reactions, but also during the overall combustion process. Of course, there are limitations. So first of all, we need optical access. That's important. And so for example, one example, if you consider Rayleigh scattering, that means the scattering of our laser light by the molecules in our volume. Laser scattering means the detected wavelength is the same like the excitation wavelengths. The idea is the detected the scattered light comes only from the molecules along the pathway of the laser. But if we have windows, if we need a closed vessel, we always will have scattering and deflection and so on at the windows, which then of course have big influence to the outcome of our measured scattering light. So it's always important to consider, is the test vessel proper for the measurement method I need to apply. And so what we have discussed yesterday with this jog tube, Yes, we can have here optical access. We have quite long observation time, so 2 milliseconds up to 50 milliseconds. However, we have only, in this shock tube, or here we have a shock tube, so we have not the possibility of averaging. So we have one shot, and then after 30 minutes we can perform the next experiment. And then, of course, the question of reproducibility. So even though it may be reproducible with one specific setup, if you then want to compare it with another setup in another lab, there may be deviations we have then, of course, to consider. But then we can use the whole range of techniques here for this. So we have discussed it shortly also for the flow reactor, where we have access, so we can use laser-based diagnostics also inside a flow reactor. Of course we have to adjust our setup then to have access here, but it's very, very often possible, even though when we have to use closed vessel systems. So the need here is, of course, we need to have a reactor. So our shock tube, RCM or flow reactor, engine, whatever. We need then something we want to examine, and which we can examine using proper laser technique. So LIF, for example, is only possible with selected species. So OH and O, nitric monoxide, can be used easily. CH is also possible, but if we want to, example, use LIF for H and O atoms, it's getting more and more complicated. 2 photon techniques have to be used. So we need, for the proper species, first of all we need a proper species, and then of course we need proper light source. Lasers are quite expensive. We are talking about several $100,000 of euros for very sophisticated setup. So of course this is then the crucial part. You can do whatever you want, but you have to pay for it. So it's quite critical. Then for our elementary reactions, we need normally something like a photolysis source. And of course, finally, we need a detector, photomultipliers or photodiodes, so quite simple. And then we have CCD cameras, and today more and more common are CMOS cameras. They have better detectors, but of course other limits. Again, here on the detector side, we are also talking about money. This is also crucial. So photodiodes, photomultipliers are quite cheap, but if you want to have a very fast CCD camera or have a camera where you can measure high-speed videos, you have to pay for it. So the classical photolysis sources are also lasers. The old fashioned way is to use excimer lasers, but so you have to get them because the most of the newer lasers are for example, Niranjan lasers. But of course, you have to consider that you get proper wavelengths to initiate your reaction here. Then, so I will not go too much into details concerning spectroscopy, but at one or two positions we have, of course, have to discuss it. So your molecule is normally in its ground state, so at room temperature, so 300 K. So, and this electronic ground state here is separated in different vibrational states, depending on the temperature. There is an Boltzmann distribution here, and then this vibrational state is, in case of a molecule, of course, then also eventually separated in rotational states. So you have a Boltzmann's distribution of your molecules depending on the temperature you have, and then you can excite them with a laser. So the energy difference is, of course, related to h times nu, the frequency of our laser. So you have to use a proper frequency to match it with the energy difference between the two levels you are interested in. So you excite your molecule to an excited state. Here you have then energy transfer processes. So these excited molecules collide with other molecules. They change their vibrational state, they change their rotational state. And then after a given time they fall down from a different state, emit some light, fluorescence light, which you then can collect. Or what can happen is that they move to another electronic state. Here it's an excited triplet state, and here they may stay much longer, for a longer time, and then they fall down to the ground state, and so this is then called phosphorescence. So we have different transitions here which we can consider, and always, of course, it depends on our molecule. What is the proper way here? But this is the general assumption. We do not have only scattering from our molecules. There can, of course, be an excitation and so on. Another principle is the absorption spectroscopy, use of Lambert-Berge law. So we have a light source and send it to our detector, and the intensity of the light behind the detector depends on the length of the cell here, the concentration inside the cell of our molecule of interest, and an extinction coefficient, so, or absorption coefficient. So what we see, if we use proper wavelengths, the light is absorbed depending on the concentration we have. So this is then normally the quantity of interest. Very sophisticated technique, but very common use in chemistry here is the atom resonance absorption spectroscopy. So here we are talking not about molecules, we are talking about the absorption spectroscopy with atoms, and this we can use also with our classical shock tube here. Here we have a specific light source. We have a shutter here, and then we have an solar blind photomultiplier at the end. So we send our light through this volume and probe for specific atoms, depending on the wavelengths we use. So this can be used for a broad range of atoms. So it based on some work from 1965 where they used a light source for H atoms, and you see 121 nanometers here. We are in the far UV region. It's very high selective due to very high absorption cross section. So you really very, very small amount of H atoms to detect them. So 5 to the power of minus 13 mole per cubic centimeter. This is a very low number here. So we can examine or use it for a lot of reactions, but finally the drawback is we need a calibration. So we have a classical absorbance here as a function of time. But to come from the absorbance to a number of H atoms, we need then of course a calibration curve, and here we see the modeled H atom concentration via absorbance under similar conditions. So this is then always the crucial part. Get your concentration from the measurement, and this has to be done frequently. So if we have different pressures, for example, of course the absorbance is then here influenced too, so this has to be considered. Here we see the absorbance as a function of number of atoms. As some careful background work necessary. So the advantage is we can produce atomic products quite easily. So if we have a hydrocarbon and want to separate H, so it's quite easy to perform. We can examine the consumption in bimolecular reactions. So this reaction in detail I will explain later on, so we can use it for more complex reactions. One disadvantage is we need high purity, so everything produces H atoms, so we have to clean our reactor carefully. Shock tubes need to be very clean and highly electropolished, and we should use only very, very low concentrations because the method is so sensitive. But here an example. So we have CH plus N2 gives HCN plus N. This is the reaction we want to examine here. And so you see we have a quite complex setup. We have a classical shock tube. So driver part to driven part. We use a krypton fluoride laser to initiate the reaction to form our CH radical. We use a laser system to produce laser light at 431 nanometers. to measure the CH absorption. And we can use this also to examine the atomic resonance spectroscopy, absorption spectroscopy for N atoms. Of course, we need a proper mixing system, but the sophisticated part is here to have a proper timing. Okay, here we have a continuous wave laser system. That's maybe not the big problem, but we need to trigger this laser, eventually this laser, the camera system, based on specific timing. So we need to know exactly when our shocks are at this position, and we need to know exactly, okay, is there a delay between trigger signal and the laser pulse here and the laser pulse here, the gating of our camera. So it's quite complex if we use multiple techniques. And this is just for one single reaction. So here you see a sketch of a flow reactor, and here we initiate the photolysis with UV lamp absorption. So we have seen this image before. So we have a flow reactor, so the flow is moving through in this way through our reactor, and here we have optical windows to examine the flow before and after the reaction volume we have here. So here we use a laser again, an argon fluoride excimer laser, to initiate the reaction of interest in our flow reactor, and we use then an HD xenon high pressure lamp to produce ultraviolet light and in the visible range, and then we measure the absorption of the light inside our reactor, and here the absorption is mainly from HO2. So here we have a premixed NH3O2 mixture in our reactor, flow reactor, and finally we measure then the HO2 concentration to get some information about the reaction of interest. So, example here we have the HO2 as a function of time signal. So we see that it increases when the flow enters our flow reactor, and so the reaction initiated, and finally a saturation level is reached here. So of course this technique, which is quite simple, has disadvantages. First of all, many species can absorb here a light, can have an absorption cross section in the specific region. So advantage is you can use it for every species, nearly every species. However, if you have several of them in your reactor, it's quite difficult to separate them, so the spectral overlap is the disadvantages. And what we do today normally is TD-LAS technique. So we have specific lasers we use. So we have only very small wavelengths which we send to our test vessel. So tunable diode lasers are used here. They are very cheap because they are used for telecommunication, in our days, and the advantage is if we can use it for a lot of different wavelengths. So we can use for each molecule one specific laser with a very narrow wavelength. So the spectral overlap problem can be avoided then, of course, because we can examine the absorption by different molecules within one experiment. So then, of course, you have to consider something like temperature dependency, pressure dependency. I said in the beginning, the absorption depends on the concentration of our molecule. But also, this, of course, is then related to temperature and pressure. So here for this CH3O2 example, it's visible how the cross section decays with temperature. So you need to know precisely how this change for a precise measurement. So here's an example, and quite easy example. So the absorption cross section for hydrogen peroxide as a function of wavelengths. This you have to consider. Here it's for HO2 as a function of wavelengths at room temperature. So you need to know a lot of details if you want to perform your measurement really precisely. And here you see it can be quite complex. So here we have the temperature dependency for toluene, which looks quite confusing. We do not longer have an single linear relation of our signal. So when you change the temperature, you can see how the shape of this absorption cross section as a function of wavelengths change with temperature change. So, and finally, of course, you can use these techniques combined. So we have discussed this already very shortly. So here we have an reactor where we initiate the reaction with a neodymium YAG laser. Then we can use a 308 nanometer for laser-induced fluorescence and a laser to examine the OH radical. And here for HO2 we use a diode laser for the absorption measurement. So we can probe within one reactor several molecules to get more information about the reaction. Continue with cavity ring-down spectroscopy. So here we use a YAG laser and a so-called optical parametric oscillator, an OPO, which then produces the final wavelength of interest. And this we then can send into our cavity here. And the main idea is here we have highly reflective mirrors here. So our light is then reflected very often within our cavity. And we measure finally with a photodiode the intensity of the light which comes out of the vessel. So the idea is here our light enters, and depending on the gas mixture inside the cavity, there can be, first of all, there has to be a molecule which can absorb this frequency, and if it's there, you can see that the light hitting our detector, of course, decays as a function of time, so with each reflection or after each reflection, the intensity decreases because it's absorbed, or some amount of the light is absorbed by the molecules. So we get this graph finally, so an exponential decay of our laser light, and so we can use this technique to measure very, very small concentrations. So it's a very high sensitive method. It's not dependent on the initial laser intensity, so shot-to-shot variation concerning the energy of our laser has no influence here. So we can repeat the measurement quite often, so we can maybe even after several milliseconds we can perform the next shot. So it has a lot of disadvantages, but so first of all we need a proper light source, a proper laser here. This is today no longer the big issue. We need proper mirrors here for this specific wavelengths, but finally the main problem is it's quite expensive. So we need a laser, of course, and we need proper mirrors here, which together is quite expensive compared to other techniques. So laser-induced fluorescence. This is typical workhorse for combustion experiments. Here we have a more simple setup. So we have our ground level. Our molecules are normally here in this ground level of the this electronic state here. Even at combustion conditions. Then depending on the temperature, they may be in different vibrational or rotational states. So we can use in classical Boltzmann distribution here to get information. So how many OH atom we assume in which energy level. And then we can use a laser with a proper frequency to excite molecules from the ground state to the upper state. Then here we have energy transition in the upper state. And finally, after a specific time, this molecule falls down to the ground state and emits a light with a frequency depending on the energy gap between the specific level here and the specific level there. So we excite our electron inside our molecule from one specific energy level to a higher energy level, and after a given time it falls down, we can detect the fluorescence. So again we have to take care. So this is a very narrow band laser normally. We can also use broadband lasers, but normally this is a narrow band laser. So this has one specific frequency. However, the emission spectra consists a lot of lines or even bands. So we have a broad detection region here, and it's quite difficult, for example, to perform quantitative analysis here due to the processes leading to the distribution of our molecules in the upper electronic state. So when we go a little bit more into details, here we see the electronic ground state. We see here different vibrational levels. V equals 0, V equals 1, and inside these vibrational levels we see different rotational levels. So the population here depends, of course, then on the Boltzmann distribution. We excite from one specific rotational level in one specific vibrational level in the electronic ground state to this upper electronical state. We reach one specific level. This depends on the laser wavelengths we use. But then, of course, we have a distribution here due to collision processes and other processes. We can have pre-dissociation and so on. It depends really on the system we examine, what is happening here in the upper level before finally the electron falls down. So, and even though if they come from one level here, they can fall down into several levels here. So only this leads to different frequencies in our emission spectra, so it can be quite complex. But we can use this technique, for example, here in our flow reactor. Again, we use a krypton fluoride laser to initiate the reaction of interest. And then here we use a neodymium laser to examine OH live. So this is one specific transition we excite here to have access here. That's the advantage. Neodymium laser plus dye lasers are quite cheap, and this detection wavelengths is quite common in our days, or this excitation wavelengths, sorry. So how does it look like? We have our high pressure cell. We use this excimer laser for excitation or initiation of the reaction. Here we have our YAG laser dye laser system to produce the light at 281 nanometers. We send this through our cell, and in this example we have quite a simple photomultiplier which then collects our fluorescence light, which is then selected 90 degrees or perpendicular to our normal to our laser beam. So then for this setup we examine OH, and we can see, for example, the intensity of the fluorescence light as a function of time. So here for two different temperatures and pressures, and this then can be used to examine in detail, for example, here elementary reactions. More popular, maybe more insight can be yielded using planar laser-induced fluorescence when we consider combustion processes. So we have a laser source, and then we use a laser system to produce a laser sheet. So it has a given height up to several centimeters, and it's normally very small, so in the range of 100-200 micrometers. So we have a sheet which we send to our probe volume, our flame, for example, our combustion cell, and then 90 degrees or in a specific angle to our laser, we have a camera where we can detect the emitted fluorescence light. And normally we use a filter here to get rid of the scattered initial wavelengths of the laser source. So finally we get information about the fluorescence as a function of the position inside a flame. So here an example. So this is a photography of the flame at different equivalence ratio. We see here quite blue flame, mainly only CH we can see here. Then you see how the structure and the color changes. So on the right hand side we have a yellow flame again, so a lot of soot formation eventually. And so we can measure, for example, the temperature in this case using so-called two-line thermometry. So we have the temperature here, signal strength, and so on. And so how does it work? We use two lasers with two specific wavelengths. Maybe I go back here. So we excite two selected ground states here to two selected rotational levels in the lowest vibrational level, normally in the electronic ground state. And so we have a Boltzmann distribution, this we know. So if we know the initial temperature, so we know how many, or we want to know the temperature, and therefore when we measure the intensity at one specific wavelength and a second specific wavelength, we get information about the Boltzmann distribution in the ground state. And this then finally gives us information about the temperature in the inside the molecule or inside the combustion chamber. But again, you see we need two laser systems, so two YAG lasers, two dye lasers, quite expensive system together with two ICCDs. So then we can come to laser induced incandescence. This we use for examination of soot formation. So we have particles in our flame, for example, here, and we heat these particles up with a laser to a specific temperature. They start to glow, and this glow light then can be detected. We can yield several information about these particles from this emitted light. So we can measure first of all soot volume fraction. We can get information about the particle size. So we can perform planar measurements. We can perform temporal resolved measurements. Of course, there are limitations. There should not be too much soot, otherwise we will face some problems. We need high power lasers, so quite expensive again. We need proper detectors with short gating time. And of course, we have to consider, are there other excitations? For example, if we have classical hydrocarbon flame, or here with precursors like benzene, there will also be broadband fluorescence. So we have, in addition to the light from the incandescence, we also have fluorescence light, and this we may use proper filters or proper detection system to separate this. So the typical application is examination of soot growth and destruction in laminar flames, or soot emission, for example, from diesel engines. So the idea is, so we heat up our soot particle, and then we detect the thermal radiation as a function of time, for example. And but what we have to consider is, of course, when we heat up this particle, we have some vaporization, we have heat conduction, we have thermal radiation. This then, of course, finally influences the temperature of our molecule. But if we do it properly, we can calculate the temporal profile of our incandescence as a function of temperature. So here the only mathematical details for today. So we heat up our particle, and so we want to measure the radiation, which is the function of temperature, of course, and we have to consider vaporization, we have to consider heat transfer. So it's possible, or it's necessary, to have an accurate description of the heat mass transport kinetics if we want to get the proper outcome here. But it can be used also in quite complex geometries. Here it's again an optical accessible engine, where we use a laser sheet here to heat up our particles, and we can use a mirror here to measure the emitted light. So we get information, for example, about the growth of the soot particles, the position of the particles inside our diesel fuel here, diesel combustion process. We can, when we combine it with, for example, laser-induced fluorescence from the PAH, we can see the area where we have soot. So inside here we see the precursors leading to soot, but the soot signal we can see only here in the outer region. So this is a classical image here for a burner. So the reaction starts somewhere here, and finally we come to the soot region, and so we can use a laser sheet somewhere here, or a laser beam, and then we get a radial intensity profile at a function of height, for example. So we can get qualified information about the amount of soot here, together again with the fluorescence of PAH, to examine the soot formation process in detail. This we can also mix with Rayleigh scattering, so-called Rayleighs. So you can see now the setup is already getting quite complex. First of all, we have again a neodymium YAG laser here. And then we produce a train of laser sheets here to use the whole energy range of our lasers. So we extend the temporal length of the laser, increase the energy per time, but the total amount of energy stays the same. And so we can then examine the incandescence with one camera and the scattered light with another camera, with using proper filter systems. We get several information within one experiment. Here we can use this for temporal resolution. So it's a quite fast process. So we are talking about nanoseconds up to microseconds. We need between several consecutive experiments. So this is a typical outcome. So we have one signal so measured here at different height above the burner, and you see a comparison with the calculated signal, so it's quite good. So we have we yield very precise information here using this technique. So I continue with gas chromatography and mass spectrometry as a final part for today. So we won't have a break, but I think maybe we need a maximum 30 more minutes, plus the questions discussion afterwards. So most of the this lecture you have survived already, so the rest is maybe also handleable. So gas chromatography, or mass spectrometry. So we leave now laser diagnostics. We have here two techniques to separate gas mixtures using different methods. So we get information about which species we have, so the molecule of interest, and we also can get quantitative information, so how much of each molecule we have. Of course it has some disadvantages, so we have to catch our probe, and if we, for example, want to extract some molecules from our gas phase and send it to a gas chromatograph, it will cool down, some reactions will continue, so the mixture at the end of the gas chromatograph is maybe not the same we have extracted from our gas, our flame, and we don't have any time resolved information directly, so we have to repeat the measurement very often at different times, for example. So the idea is quite simple. We have a sample injector, we have a column here with a carrier gas, and at the end we have a detector. So we have something like a so-called retention time. So within this column, the different molecules we inject need different times until they reach the detector. So simply speaking, the lighter molecules are faster here than the heavier ones, but of course it depends on our column we use. But nevertheless, at the end, we want to separate our molecules using this column. And this can be done for also complex systems. Here we again have a shock tube. Here we have a sample port in our region of interest. And here we use two different columns, one for lighter hydrocarbons, one for heavier hydrocarbons. So we get quite sophisticated information here. And here this is then coupled to flame ionization detectors. So we can then not only separate the molecules by the GC, using this FID we can also determine the amount of molecules we have. So we have quantitative information about how much molecules we have and what different molecules we have. So it's quite helpful method. And this is one of the advantages if we have a proper reactor. This can be automatic. So this can be done several times in repetition. And we yield a lot of information here. Of course, this depends then on our reactor. So here the principle of this flame ionization detector can be seen. So we have the column with our molecules. We have hydrogen here to have a stable flame here. And then when our probe molecules enter this flame, we can measure the ionization inside this flame. So we have an electric field here, and depending on the combustible, depending on the molecules we have here in this flame, we see a different response of the ions here in this flame, and so we can then finally collect or get information about what molecules we have in what quantity. So what we get from the column and the intensity here then of the response of the amount of ionization gives us information how much molecules we have. Okay, this I skip. So when we look at a classical GC, you can see here intensity, for example. So we can separate a lot of different molecules here, again as a function of time. So it depends of course on our column which molecules come first, but here we have some bigger hydrocarbons separated. Here we see only the mass of the different molecules. So it's quite interesting. So mass spectrometry as a last technique we want to discuss today is is of course more complex, but gives us more detailed information about the mass of our species inside our reactor. So the idea is here we have a reactor, our reaction takes place here, and we suck out some probe volume out of the reactor, put it into our mass spectrometer, and so then we ionize our molecules here, and depending on the mass of the species we have, so these ionized molecules have to flow through an electrical field, and then of course they will be, depending on their mass, they will be detected at different positions. So we have a 2D time and position sensitive detector, and then can separate the molecules by the mass. So it's quite easy, but of course we have to consider, so we suck out some molecules here, and we need some time until they reach the detector. However, the advantage is we have nearly vacuum here inside this cell. So the probability that the excited or the intermediate species will collide again, further reaction will take place, is quite low. If we use a proper setup here, we can really get the information we want about the reaction of interest. So here's an example. So they used the advanced light source in Berkeley, combined with this mass spectrometry. So even very sophisticated measurements are possible to for a simultaneous detection of multiple masses under engine relevant conditions. It's a very, very helpful technique to get detailed information here. So we get additional information when we then consider also the time of flight. So how long need these molecules until they reach their final destination. So you can see here, if we use a linear time of flight mass spectrometer, we cannot resolve this broad peak here, but if we have a modification, so-called reflection time of flight, you can see here 3 or 4 different peaks. They even have a fifth one here. So and the difference is just 1 Dalton here, so 1347 and 1348. So it's has a very high resolution on these techniques. So I'll come to an end. I'll come to an end with the last topic, flow visualization, particle image velocimetry. This can be used to examine the flow field. So we add normally particles, either solid particles or liquid particles, to our flow, and we have a use a laser system to follow these particles. That means we have a laser sheet, then we have me-scattering from our particles, and after a given time we send a second laser pulse to the same system, and our particles have moved depending on the flow field, and so we get two consecutive images of our flow field with a given time distance, and using some mathematical methods we then finally can follow the different particles in the flow field, and for each volume we can then calculate the velocity of the particles, and normally the assumption is correct that the velocity of the flow field is equal to the velocity of the particles. So we get then information about the flow field in detail, and it's the advantage, it's a quite simple technique, and we have an 2D configuration. Here you see the vectors of the flow field, and here it was combined with an OH measurement. So we have we see here more or less combustion taking place. So this is then of course necessary if we want to examine the interaction of the flow field with our flame, or like Professor Sahoo has said in the morning, there can be extinction, for example, if we have too much strain, so the flow field is too intensive. So this can be examined, for example, with combination of PIV and OH LIF. Here this is done for a swirling flame, so the flow is coming from the bottom, and then here we see the flow field of our flame. So the technique is quite simple. First of all, you need a proper laser, or laser system, either two single lasers or one laser which is capable to be operated in a double pulse option, that you get two laser beams in a given time distance of microseconds normally, and each laser pulse should have a very short pulse duration. So it's quite easy. So you get me-scattering. You may see the white particles here. It's very sensitive technique. And then the problem is you get two of these images. You have maybe thousands of particles on your image at one given time, and the second image a little bit later, and then to correlate the change of position of each particle. But here this is nowadays standard, so normally you have proper software, and this is done more or less automatically. But of course you have to double check here, is everything correct? But with two images you can get quite simple information about the flow field. So that's for today. Do you have any questions?
So, sir, UV lamp absorption techniques.
Mm-hmm.
Can it be used for all kind of reactions?
First of all, you need a molecule which absorbs. So then this has to be considered. In principle, yes, but the correct answer, it depends.
So it depends on the species we are going to detect, and for that we need to use different kind of lasers.
Yeah, so the modern application is using these TDLS lasers. So the modern communication lasers we have at several wavelengths. So we can use it for specific molecules, so ammonia, hydrogen, NO, and so on. Mainly water. So that's the typical application.
And the YAZ laser, you say it's used for what purpose?
Pardon?
YAZ, YAG laser.
Yeah.
So for what purpose it is being used?
So there exists several so-called solid-state lasers. Neodymium YAG is just one possible realization here. There are others, deuterium lasers and so on. So you find different solid-state lasers. The advantages, they are quite cheap and quite reliable in our days. So these X-hammer lasers, which I have shown here, were more popular in the past. In our days, we use more these solid-state lasers. And neodymium YAG laser produces light at 1064 nanometers. So that's the fundamental line, and this can be then frequency doubled to 432 nanometers. And for OH, for example, we use then a dye laser with rhodamine 6G. So we yield then, when we use this 432 nanometers of a dye laser, we yield after the dye laser process 560 nanometer. This is then again frequency doubled, and we get light at 280 nanometers, which we then use for OH. Yeah, so another application is you can frequency triple your neodymium YAG laser, and you get light at 355 nanometers, which can be used for other dye laser excitations. For example, when you want to go to NO fluorescence, you need 226 at the end. So using coumarine in your dye laser, get 450, frequency double 225. Or use it directly for hydrocarbon flames. Maybe you can see CH already with 355. And you can quadruple this laser light, 266 nanometers. So you have 4 different fundamentals which you can use for different applications, and you have really high energy lasers in our days already, so range of joules per pulse. So I have shown you on one image how they separate this laser, this very short laser pulse, and so they lengthen it, so to decrease the amount of energy per time. But then you can couple a very high energy into your probe volume for example, Raman measurements, Rayleigh measurements. So it's for me, this is a typical workhorse in our days, the neodymium YAG laser.
And for the same purpose, I hope we are also using krypton chloride laser here.
Pardon?
Krypton chloride laser.
Yeah.
It's also used for the same reason for OH detection.
Yeah, it's so the 00 band of OH is at 208 nanometers, and then 10 is 281. So where we use this normally this neodymium YAG dye laser system, and at 2488 we can use predissociation LIF. So there's a 30 band So we can also use 248 nanometers to examine OH radicals.
And when you are using this laser-based diagnosis system, whether it is LIF, PLIF, are you getting any kind of quantitative analysis out of that? For example, when you are using GCMS, you said we are getting quantitative and qualitative analysis.
Yeah.
Is the same thing happened with laser-induced fluorescence, LIF or PLIF?
This is a difficult question. You can, it depends on the molecule, first of all. For example, for OH is quite difficult because you have a lot of energy transfer processes. So, as I said, you excite with one specific wavelength, but you get an excitation emission spectrum which is very broad. So, because you have energy transfer processes in the upper electronic ground state. So your excited OH molecules collide with water, collide with nitrogen, collide with other molecules, and each collision changes the electronic, the energy level of this OH, and when then the OH molecules fall down to the ground state, they fall down to different levels in the ground state. So you have a lot of lines you see, and so you see, so you excite, for example, at 281 point, maybe 2 digits after the comma, very precisely, and then you get light in the range from 210 to 270 nanometers, 310 to 270 nanometers. And so the intensity of your fluorescence light does not depend only on the amount of OH you have, but also on the energy transfer due to collision and so on. So this is quite difficult. So for OH, normally you see only qualitative results.
TIDLAS is available for all the species?
No, this is then mainly the work of Ravi, who spent a lot of money to find proper lasers for proper wavelengths. Yeah, so as I said, these are mainly telecommunication lasers. You get more and more wavelengths here, but of course not for every specific wavelength.
Another thing that while measuring in TIDLAS, so is it the ray of the laser or it is converted to a seed?
Pardon?
Yeah, the laser is applied as a ray, means a straight line, or
Yeah.
it is converted to seed?
No, this is a line of sight technique. So you measure the absorption, and so you send a small line, and you send just a line through your vessel, and then you measure the absorption along the length of your cell.
How to ensure that the mixture is homogeneous after the combustion process, so that a line only gives you the best result, not a seed? I think a seed can give you the average value of that one, or a volumetric analysis can give the better value.
You mean so the application of this TIDLAS technique for combustion processes? Yeah, that's the critical thing here. You have to have homogeneous conditions along the length or the way of your laser beam. So when you want to get quantitative information. So you're absolutely right. If you look into a flame cone where you have a change of composition, then you see only quantitatively, is there absorption, how much absorption there is, but you cannot resolve it in a way that to say, okay, I have this amount of absorber here. So the crucial criteria for a quantitative measurement is that you have a homogeneous mixture at known temperature and pressure.
So, sir, this LIF or PLIF compared to GCMS, will there be any change in result or variation in result if you are collecting the sample and using it in GCMS rather than going for LIF or PLIF?
First of all, it's so LIF is mainly used for the smaller molecules. Okay, we can use it for the big hydrocarbons too, but if you are interested in the reaction zone, you mainly use it for the smaller molecules, OH and so on. While GCMS gives more information about the more stable molecules you have, the larger molecules. When you compare it then maybe with mass spectrometry, where we also can measure the smaller particles, we always have to consider that laser-induced fluorescence is an instantaneous measurement. We look directly at the position where the chemistry takes place.
But here we are collecting it and then...
Yeah, and then there maybe is a change of mixture composition. Some follow-up reaction can take place and so on. So this always has to be considered. Therefore, it's difficult to say which one is better. We need both of them.
Normally you used to collect the sample and then go to GCMS and test it.
Yeah. So gas chromatography I would recommend if you have stable molecules which do not react along the column. It takes a long time until they reach, for example, the flame ionization detector. First of all, you separate them by mass, and then you check how much you have at which mass. So this is very precise. So you can go down to parts per billion. This is very, very precise. However, if you take it from a flame, what you measure at the end is maybe not identical to what you have sucked out of the flame. So here an MS is much better because you have a vacuum behind your nozzle, so most of the reactions no longer take place because the probability of collision is quite low. No further questions?
With leisure people shown interest.
Pardon?
With leisure people have shown interest.
Okay, so it's time for a weekend.
Yes.
Okay, so thank you very much.
Yeah.